Good morning. Today is February 4th, Tuesday, 11 a.m. Lecture 4, CS 797K. This lecture is on RAID levels and redundancy. So let's see where we are at. So we have just finished basic parity bit detection protection. That's Hamming code in the last lecture. And in this lecture, we're going to discuss about basic RAID parity. So what is RAID? So this was the term coined famously, I mean, coined in famous paper by Gibson in 1986. So RAID, it's redundant arrays of inexpensive disks. Yeah. Yeah. A case for redundant arrays of inexpensive disks. That's the full form of RAID. So it's like array of disks. It's like stacking disks and storing the data, like either duplicating the data or storing it in stripe wise or anything. So it's like just array of disks storing data. So acronym later retconned by to independent disks. Yes, inexpensive, so later it was renamed to independent disks. So this was the paper first published on RAID. So if we open the paper, let's just see what it is. Yeah. So a case of redundant arrays of inexpensive disks. So this was written in 1987 by Gibson. So some code, citations, and where is it? That's okay. So this was the paper. If you are interested, you can just go ahead and look what was in the paper. So he just explained about 5 different raids in the paper. So technically 6 raids in the paper. So you can just go there and look at the math and everything in detail over there. So this lecture is just taken out explaining some important stuff out of the paper. So let's just get back to our lecture now. Yep. So the paper predicted an I/O crisis, input-output crisis, as CPUs and memory sizes were growing much faster than disk sizes. So at the time, like in 1987, so there was a study which explained the sizes, the memory sizes were growing much faster than disk sizes. So the memory sizes were like exponentially increasing, like for every 12 months, that was like double the size of the previous 12 months. So that's the reason the disk sizes should be increased as well, or should be, you know, stored the data without losing it, or even if it lost, if we lost the data, there should be some method to retain our data back. And classified existing approaches for improving performance and reliability of smaller and cheaper drives. So that was later renamed it into independent drives. It's not inexpensive now. So defined 5 RAID levels in the paper, which we're going to discuss in this presentation. So calculated theoretical performance, overhead and reliability. So we'll check what these terminologies in the slides later. So IOPS, input outputs per second. So per second, a simple measure of performance, how many inputs per second or how many outputs gonna retrieve in 1 second. And MTTF, that's called mean time to failure. So that's the expected lifetime. So by the start of using a RAID, so by how much time it's gonna fail, or it's gonna stop, we're gonna lose our data. So that's called MTTF, that's mean time to failure. So calculated by testing a lot of drives from some time t. So they have taken time t, like 2 days or 3 days or 1 month or 1 year, that's time t. So that's by testing a lot of drives. So they're going to use the drives for that time period t, and they're going to calculate MTTF by the time lost, the data that they lost the data. So it's by this simple formula, 1 by fraction of drives that fail within T. So in the time period T, how many drives that's gonna fail? If it's 2 drives, then it's 1 by 2. If 3 drives gonna fail, then it's 1 by 3. So these are drives, or disks we say. So we have in one RAID we have multiple drives or disks. So we're going to calculate how many disks or how many drives that fail in a given time period T. So 1 by 100, that means if 1 by 100 drives fail in 2 hours, so one drive out of 100 drives fail in 2 hours. So that's 1 by 0.01 by 2, that's 200 hours. So it's within 200 hours, that disk won't be used. Like in 1 week, the disk will be corrupted. So just don't buy that drive. So MTBF, that's called mean time between failures. That's the marketing strategy now they are using to sell their discs. So a failure is a failure. So if it's failing in 1 week, it's failed. It's not like first failure and second failure. They're just calculating the mean value and they're just putting out, showing out in the marketing right now. So that's like recoverable errors they are saying. That's just the marketing strategy. So the MTTF is the actual measure. So MTTF, so that's the measure we need to look at, not MTBF. That's the marketing strategy they are taking now. And it's MTTR, mean time to repair. So how long it takes to notice, repair, and rebuild the data on your failed device. So if there is a failed device, so how much time will it take for us to recover the data in that drive in the RAID? So that's called MTTR. We can calculate MTTR as well. And it's like rebuilding the data on a failed device. So how long it takes to notice, replace, and rebuild the data on a failed device? It's MTTR. So this is the terminology. Any questions in terminology? It's a simple metrics we're using to calculate the performance. Yeah.
What does that look like then, if it's not like immediately obvious?
Oh, it's
So when they first started that, they just had a bunch of disk drives
Yeah.
in a box. And so they would have, they'd be running the thing, they didn't have any fancy logging, stuff like that, and things like that. So they wouldn't necessarily know the drive had failed.
Okay,
So it actually had to take someone to go, originally he pictured that there would be some sort of a log from the host thing was getting IO errors. Someone eventually look at that log, see there were IO errors, recognize there's a problem, go pull the drive up, fix it. Right?
okay,
And replace it. And later, they started adding extra drives in there so that the subsystem itself would instantly recognize there was a problem, throw that old drive out, not turn it off, basically, pull a drive from another spot, spin it up and use it right away.
okay. So nowadays, it's not like as big of a deal. No.
Yeah, it's not, it's especially not as big a deal now because we have solid state drives, which are a lot faster than those spinning disk drives, where when they invented the algorithm. So,
Okay.
last slide, asks if rate is still relevant. Stole it.
So disk strapping. So this is RAID 0. We're just taking disks D1, D2, D3. It's actually starting from D0. That's the wrong terminology. This was stolen from Wikipedia. So in Wikipedia, yeah, they were doing like D1, D2, D3, but it should be D0, D1, and D2. So disks should be starting from 0. So you can take any number of disks and you can write your data in stripes. So across multiple disks. So instead of writing data in one disk, we are writing the data in multiple disks. This A1, A2, A3, A4, and then B1 starts, B2, B3, B4, and so on. So writes data into multiple disks. So this is called stripe. And multiple stripes, we have like, we're writing data in multiple stripes. And again, C1, C2, C3, C4, and so on, so forth. And with each additional disk, so let's calculate max possible performance increases. Yes. So the performance will be increased. One drive, X input outputs. So then N drives would be X times N input outputs. Simple. And this is the reliability. The reliability will be decreases. Like one drive, x hours. So n drives x by n hours. So since the denominator is increasing, so we get MTTF reduced. So it's called MTTF group equal to MTTF drive by D. So the outline reliability decreases for RAID 0 with the number of increasing disks. So theoretical RAID reliability, original reliability formula in Gibson paper assumes a group will fail on the second drive failure. So given, let me just write all the things here. So MTTF group. So MTTF disk squared by what's G? G is data drives in one group and C is check drives in group times G plus C minus 1 times MTTR. So we'll see like what is check drives. It's the check drive is not yet in RAID 0. We'll check what the check drives are. So this is the basic formula to calculate MTTF group and MTTF RAID. We'll see what are groups and RAIDs in later. So these are the abbreviations. So data drives in RAID. G is data drives in one group, and D by Z is number of groups, like total number of drives by number of by one group is will give you number of groups. It's simple math. And C check drives in group. We'll see RAID 1. It's just mirroring. We'll write all our data on one disk and we'll just mirror the disk onto another disk, disk 0 and disk 1. Again, that's the right terminology here, disk 0 and disk 1. So writes 2 copies of everything. It's simple. Performance is same as the slowest disk. And reliability, MTTF group. So this is a group. So MTTF drive squared by 2 times MTTR. So let's see what that means. And overhead is 100%, 2x. So overhead 2x, so it's 2 times. So that would be 100%. So like explain we are writing the same thing multiple times. So the overhead would be 100%. It's yeah. Yeah, we buy 2 drives and we'll get like half of the data stored in 2 drives, basically. And RAID 10, it's called 1 plus 0. It's RAID 1 and RAID 0 combined. So it's like, again, it's just the nested RAIDs. So we'll just write the stripes. This is the stripe A1, A2, A3, A4. But again, we have one more nested loop over here, which duplicates the things, duplicates the writes. So it's 1 plus 0. It's just the combination of RAID 1 and RAID 0. It's called RAID 10. So starts with M drives, creates M by 2 RAID 1 volumes, yes, and stripe them into a larger RAID 0. And performance, X IOPS times M drives and writes by 2 drives. So we need to write it twice and we can just read it like half faster. I mean, faster read and slower write. Overhead is 2 again, and reliability for one RAID is disk times 2 by M times MTTR. That's from the formula. Again, RAID 10, simple RAID 1. Just a second. Yeah. So it's simple RAID 1. We'll just stripe. It's RAID 10, stripe plus duplicate. I mean, it's a duplicate. It's stripe plus duplicate. So 6 drive RAID 10. So we have 6 drives. So we have 3 groups. We are duplicating. The disk. So we have 6 drives. So that means 3 groups. So these are called groups. Group 0, group 1, and group 2. We are just striping it and we are duplicating it. It's 6 drive RAID 10. So check the RAID 10 MTTF calculations. Let me just, yeah. So again, D is data drives in RAID, G is data drives in one group, D by Z is number of groups, check drive in group is C. We'll just use this formula, MTTF disk times 2, D is M by 2, and C is 1, and G, that's number of groups. We have number of groups m by 2. Again, G plus C, 1 plus 1 minus 1 times MTTR. If we just do the math, then this would be the MTTF calculation for RAID 10. It's just substituting the same thing in the formula we have seen, we saw in the previous slides. Again, RAID 2, here comes Hamming code, bit level encoding with multiple check disks. So here comes the concept check disks. Only 2 products ever made with this technology. That's IBM 353 and in 1960s, and Thinking Machines Data Vault in 1988, considered obsolete. So no one ever used RAID 2 later. Not many, yeah. So this is the Data Vault Thinking Machines. So that was stolen from Wikipedia. So that just stored 5 gigabytes of data. That's a huge thing, just storing 5 GB of data. Yeah, contained like 39 disk drives. So 32 data drives and 7 parity drives. 32 plus 7 is 39. That's just discussed in the last lecture, how to calculate the parities and that from the data drives. 32 plus 7, 39. So split data into 32 bit words, added parity and sent it to disk. So 39, 32 and 4. So 2 power 6 parity bits needed, 7 parity bits exist. So one more parity drive for check, that's overall check bit. Yep. Yeah, there is an overall parity bit. Hamming distance would be 4. So 4 minus 1 is going to be corrected by, I mean, it can detect 3 errors and it can correct 1 error, 3 by 2, 1 error. Yeah. So that's the formulas we discussed in the last lecture. So oddly, the photo caption says there are 42 drives, maybe hot spares. They may be storing some cache memory or something like that. Yeah, maybe. Yeah. Yeah. So RAID 3, it's single check disk. RAID 3, we have a parity bit right there. So it's called XOR operation, or we can just say even parities. We can, yeah, we'll get into that. What is again disk 0, disk 1, disk 2, disk 3. So it's striping, and there is a parity bit right there. So byte level encoding with n data disk plus 1 dedicated parity n plus 1. Disks synchronized. All reads and writes required to be full stripe, a complete stripe. Performance is single drive if IOs are large enough. Yes. And again, reliability, the formula, overhead is n plus 1 by n, and is number of disks. So again, RAID 4 is independent data, dedicated parity. So we have a dedicated parity in one of the disk. So we'll see like it's the XOR parity drive n plus 1. So block level encoding with dedicated XOR parity drive. So we'll just XOR A1, A2, A3 to get AP the same way. And we are writing the data in stripes again in RAID 4. Small IOs, read, modify, write. Performance, large write performance, single drive. Random or small write performance is poor. Yes, cache memory required. Read performance is good because we're just using all the disks to read the data. So we are reading simultaneously. So read performance is good, and parity drives can become bottleneck. So reliability same as RAID 3. It's just the same thing, overhead same as RAID 3. And NetApp used in FAS system in 1992. They used RAID 4 in their FAS systems. Yeah, they are still using RAID 4, but with improved calculations, with some added stuff in RAID 4. They're still using RAID 4 in NetApp. So read, modify, write. So parity. So what's parity? It's simple XOR, right? If there are like even number of ones, then it's 0, and if there is odd number of ones, then it's 1. in the output. So it's a simple parity. So we are just XORing every data in the disks. So to read, modify, write D1 with D new one, read D1 and P from media, subtract, yes, P XOR D1, add P mid XOR D new and write D new and P new to media. So it's how to read, modify and write in parity disks. So RAID 5, it's called rotating parity. So we'll just write the parity in rotating. So it's not like having a dedicated disk for parity. It's like rotating the parities. So it can be here or here or here, anywhere on the parity. So that's called RAID 5 rotating parity. So it's again block level encoding with rotating XOR parity. Yep, that's the same thing we discussed. Here you can see AP, PP, CP, DP, that's parity bits, C and D, XOR parity. And it's a better performance than RAID 3 or 4, but caching supersedes. So reads X input outputs for N drives, so X times N drives, and it's the slowest drive to write again. So reliability same as R3 and R4. Overhead same as R3 and R4, because that's the same thing we are doing here. Just we're rotating the parity instead of dedicating a single disk to the parity. So that's the same reliability and overhead. And NetApp E series in 1991 and EMC Symmetrics in 1992 used this one, this RAID 5 rotating parity. So those are some of the groundbreaking stuff for them in those years, 1991 and 1992. So they have used RAID 5 and RAID 4 as well by NetApp. So that's like two different products, and they are just marketing it like they're just throwing it out, the two products into the market using RAID 4 and RAID 5. So RAID 4 versus RAID 5, it's simple. We have parity, dedicated parity disk in RAID 4 and rotating parity disk in RAID 5. So that's the difference. See here, parity in one drive, but when it comes to RAID 5, there can be parity anywhere in the drives. And post Gibson RAID levels. So after Gibson, it's like after Gibson, there are like new RAID levels introduced. So there are people going out and doing their research. They were extending the work of Gibson, and they are adding more parity bits, or they are coming up with some new ideas to recover data in better with better performance, or better performance and read write, or better reliability and everything. So they are just extending the work of Gibson in the papers later on. So additional redundancy, nested RAID levels, non-standard RAID levels, and so on. So RAID 6, that's called double parity. So we have two parity bits in RAID 6, AP, AQ, and it's again rotating. BP, BQ, CP, CQ, DP, DQ, EP, EQ. So it's rotating, but double parity now. So it's the same as RAID 5, but it's having two parity bits in one stripe. So any RAID that can tolerate two disk failures, multiple implementations, PQ parity, Reed Solomon, which we are going to discuss in later lectures, row diagonal parity, even odd, reliability. Here we have times 3. So it can tolerate two disk failures. So if one of the disk failed, if we identify if the disk was failed, before the second disk drive failed, if we identify it and reconstruct it, then it's fine. We can use the same RAID again. But if we haven't identified, and again the second disk was corrupted, so we can't just get the data. So that's how it's calculated right there. So tolerate two disks. So MTTF will calculate for 3 failures. So times 3. This is N is the first drive failure, N plus 1. Sorry, N is the last drive. N plus 2, N plus 1, and N. These are like 3 disks failed times MTTR. So this is the reliability calculated for RAID 6. So we need to identify the disk failure before the third disk fail, so that we can reconstruct our data. If we don't, then our data will be lost in RAID 6 double parity. And again, RAID 7 triple parity and beyond. So not necessarily the standard naming augmentation argument, and NIA called it RAID 6 TP. So later on, it's like RAID 7.1, RAID 7.2, because again, if they were naming like RAID 7, RAID 8, and RAID 9, we have already discussed about RAID 10. So that's the naming contradiction they got. So they were like 7.1, 7.2, and so on. So implementation details may vary. Standard implementation, PQR parity, extends read Solomon. So we have like triple parity instead of double now. So no hardware products due to poor performance. Reliability would be MTTF group, MTTF drive times 4. It's again, it's 4 disks failure. So n plus 3, 2, 1, and n times MTTR. It's again the same formula, but instead of 3, we're now calculating it for 4. Nested RAID. So RAID 10 mirror R1 and then stripe R0, already discussed. So in the same way, we have 50, 60, and so on, because we're just nesting 5, it's called 50, nesting 6 is called 60. In the same way, we called it 10 for nesting 1. So non-standard RAID levels, again, A1, A1. So it's not like having even number of disks here. So we need to have even number of bits for storing 2 data bits, A1 A1 and B1 B1, to just mirror it. But this is called non-standard RAID levels. They were just coming up with just 3 disk drives, and they were extending it to the next level or next type, we say B1. They're duplicating it again on the first one, C1 C1, and A2 A2 B2, and again coming here for B2. So people have come up with non-standard RAID levels as well. So that's the continuation work for Gibson. So RAID 5E, 5EE, 6E, live hot spare drives. RAID G, Z, software RAID 567 with dynamic stripe width, RAID 1E, R1 scattered, and yeah, we have many non-standard RAID levels. A non-standard RAID, a RAID DP, diagonal parity, we say, diagonal double parity. So it's like in the same color. It's for the marketing people. It's just with the numbers. Instead of XORing, they're just calculating by adding the numbers. Let's add like 3 plus 1 plus 2 plus 3. It's gonna be 9. They're just keeping it 9 here. And 1 plus 1 plus 2 plus 1, it's 5. It's 2 plus 3 plus 1 plus 2, it's 8. 1 1 3 2, it's 7. They're just adding numbers instead of XORing things. So, and again, it's the diagonal parity. If you look at this stripe, if we add 3 1 1 2, it's 7. Again, the blue stripe, 1 2 2 7, it's 12. 2 1 1, sorry, 2 1 8 1, it's 12, and 3 5 2 1, it's 11. So they're just adding again the diagonal parity. So that's the same thing, or that's the same work, but they're just doing it for numbers instead of XORing things. They're just adding the numbers. So NetApp marketing picture uses decimal arithmetic. It's really XOR. Nope, it's not really XOR. It's just addition. Performs well except when double degraded. Reliability, it's same as RAID 6. So it's just the marketing slide. So again, non-standard RAIDs, it's dynamic disk pool. So it's a simple 8 plus 2 RAID 6. That means 10 drives. So each color should be of 10. Okay, so it's like having many drives, but it's 8 plus 2 RAID. Yeah, so they're just randomly scattering the disks along many disks. They were it can be done in 10 disks, but they have extended their work to 24 disks. It's the same thing. They're just randomly scattered what's this bits to different drives. That's it. So if we see like the red one, 1 2, we see this one, this color, the first color, 1 2 3, 4, 5, 6, 7, 8, 9, and 10. So that's distributed over 10 different drives. So that can be done with 10 disks, but they have just scattered it into 24. That's non-standard dynamic disk pool. So RAID limitations, conceived as erasure coding, recovers from drive disks or drive failures, didn't consider errors, which can lead to data corruption. So, so these are the limitations, and atomic writes required to multiple disks, else data corruption. Again, doesn't protect against accidental deletions. So if someone gets there and deletes the data, we just can't regain the data. We need to have backup again to just duplicate it from the backup, but we just can't get if someone accidentally intendedly deleted it on purpose. So backups will always be necessary. So there is a song in the YouTube that's like 3 copies, 2 media and 1 offsite. So for every important piece of information you have, you need to have 3 copies. So two copies in RAID and 1 copy as your backup again. And that should be offsite. That's not on RAID. Uh, and RAID limitations continuation, like performance characteristics vary widely with input output patterns, large versus small, sequential versus random. Drive failures aren't always independent, vibration, power, etc. So if we have like not SSD, HDD. So in HDD we have the disks rotating for the memory. So if the disks was rotating, I mean while rotating, if it was like fallen from the height, so the it will get vibrations, and the data might have been corrupted. So those are the drives we used for RAID. So that was one of the limitation. Drive failures aren't always independent, like for example power, vibration, etc. High capacity drives, new technology drives. So reconstruct times too long in legacy RAID levels. It takes too long to reconstruct the drives. Solid state drives, SSD have internal EDC. How many levels of redundancy are needed? So is RAID still relevant? Yes, they are still working on RAID. There are companies that are working on RAID. So it's still relevant, but we don't know what happens after 5 years. But for now, there are companies working on RAID, and there are companies that are offering jobs on RAIDs. So you can get a job on RAIDs as well. So it's relevant for now. So create some further reading. So you can go through all of these links if you like. The RAID paper, which we shown, the images, the image we have taken from this Wikipedia, and the emoji and everything. Yeah. So whatever the pictures we have shown in this lecture, so that was kept in this thing. And so this link. So that's
It's a great reader.
that's from TikTok.
Maybe not.
So bitwise operators, it's simple AND, OR, and XOR operators, as we have discussed in our very first lectures. It's a bitwise AND, OR, and XOR operators, and that's the end of the lecture. That's what intended to discuss. Okay. Oh, I don't know. We have some of that.
Post that, and so we can at least point people to it.
Let me try to open the Python file and see what was inside.
Yeah.
So you're uploading it in Blackboard now, or?
Yes.
Okay. Okay. I'll directly download it out there. And before that, we have a homework, medium homework, Hamming encode. So that's already visible to you. Let me show you what that is. So this text duplicates, yeah. So open the spreadsheet. So the spreadsheet link was given over there. So open that spreadsheet, find your WSU ID, and pick 3 or 4 of the digits from your WSU ID and arrange them so you have a number less than 2047. So convert the number to binary because 2 power 4. Add leading zeros as needed so you have 11-bit string. Add binary string to spreadsheet. Be sure to use quotes. Encode the number using Hamming 1611 technique. So the Hamming code which we have discussed in the last lecture, just take this one, this string, and just add the parity bits and encode it, and just do it to the document, put it in the document, and add the encoded code string to the spreadsheet. Flip any 1 bit in your encoded string, just flip randomly. Paste the encoded string with the error to the spreadsheet. Column E, copy the spreadsheet row and paste it in the blackboard of your submission. That's it. It's a simple thing. Just take a 4 um, digits from your WSA ID and encode it with the parities, and just flip 1 bit. So keep the encoded bit and the flipped bit in the two different columns and just upload it. And just copy the row and just paste it in your submission, and you're good to go. And in the next homework, we will try to decode that. We'll just find the error and we'll just try to get that error back into the correct WSU IDs. Yeah. So that's one simple homework. So it's example 849. So this is the binary he got, and he has added parity bits P0, P1, P2, and so on. So this is the final output we got, and just a bit flipped. One of the bit was flipped here. No. So this is the overall parity, and you can just flip any one of the bit randomly, and just yeah, it should be 1 and instead it's 0. Yeah. Yes. Count the number of ones: 1, 2, 3, 4, 5, 6, 7, 8. Yeah, it should be 0. Yeah. Okay. Yeah. Yeah.
And then I actually hit that middle, there's 3 ones in there in the middle.
Mm.
Middle one of those to 0.
Oh, okay.
Here. You
Yeah.
can go ahead, look on the spreadsheet.
Yeah. Also, okay. It's a document. Oh, here is the spreadsheet. No. Yeah. This is the Excel sheet. Yeah, you have your WSU IDs, the ID you have chosen, the number in binary, and the encoded, and 1 bit flipped. So that's a simple task to do. Any questions in homework or in the lecture? Yeah. Let me download the IPYNB file and show you what was inside. Jupyter. It's taking time. Downloads. Straightforward. Let's see. Okay. This notebook is a simple demonstration of RAID 4 algorithm. The outer list, first index represents the drives, the inner list represents the data blocks. Each data block is simple integer. Let's see. So this is the RAID 4 illustration, just for your understanding. So this is the parity we have, and these are the disks, and these are the data bits we have. Everything in hexadecimal. Hexadecimal, yep. Yeah. Yeah, so dump drives. 1207 412.
Generate detail.
Yeah. So failed 2 drives. So drive number, oh, drive 2, yeah. Here we can see that drive was failed. It's just showing zeros. We can just reconstruct the drive here, right there, using XOR again. And fails 2 drives. No, drive 2 rebuilding. And oh, failed drive 2 by rebuilding it. Okay. Corrupt the volume by rebuilding. So it's just IPYNB file showing you the RAID 4 illustration. So how if we lost one of the drive completely, how to reconstruct it. So it was just an implementation, an IPython file. You can just go there and play around, and you can just build your own RAIDs, RAID 5 or RAID 6 as you wish. You can play with that. So that's a simple RAID lecture. I guess it's time for attendance quiz. Let me stop sharing. Let me stop recording.